So in this work, we're studying the efficacy of physical side channel monitoring systems. We proposed a novel attack to hide a malicious payload into these tamper-proof systems. This is a collaborative work with Rutgers, Georgia Tech, and CISPA. So what are physical side channel monitors? Let's assume that there is a microcontroller under protection. Physical side channels can be acquired from the device. It can be either a power side channel or could either be a EM side channel. And the collected signals will be used to track the program executions in the microcontroller. These are a couple of advantages of physical side channel monitors. They meet the real-time constraints of the device. They impose zero overhead to the device. And finally, they stay isolated from the device, so they will not be targeted by the same attack vector. These are all essential for embedded systems. Over the past few years, the physical side channel-based monitoring solutions are becoming very popular because of these advantages, both in the academia and in the industry. But the recent emerging studies on the adversarial robustness of machine learning models put the security of these systems in question. Are physical side channel monitors as secure as they are claimed to be? To answer this question, we assess the vulnerabilities of them against attacks like adversarial machine learning, but with constraints. So specifically, we propose a novel attack against the power side channel-based monitors. Before diving into the attack, let me give you guys a high-level motivating example. So let's assume there is a benign program in the form of a control flow graph. Its corresponding power side channel signal looks like this. An adversary intended to inject a malware into this benign program, so he can inject it as a whole. However, the side channel monitor will output a confidence score of only 0.77, which is far below the detection threshold, so it'll be detected. Alternatively, he can split it into independent pieces and distribute them into optimized locations in the program, like this. And in this case, the confidence score is 0.99, and is above the detection threshold, so it can bypass the detector. Now that we have the high-level understanding of the attack, I will introduce the details. So first, the system model. A typical side channel monitoring system looks like this. So there is a microcontroller interacting with a physical system. A side channel probe is constantly acquiring side channel signals from it. And these signals are used to train a detector. And the trained detector will be deployed to detect any malicious behaviors. We assume the following attack model. The adversary wants to compromise the normal operation of the victim system by uploading a maliciously modified program. At the same time, he needs to remain undetected. There are a couple of constraints for the attacker. First, there's no way for him to directly manipulate the feature space, which in this case is the signal points. Second, no live query into the model is allowed because it will interrupt the normal operation of the system. Given the system attack model, we present our attack. It contains 3 steps. First, we will build a substitute setup that we will be used to optimize the attack. Like where are we going to inject and what are we going to inject into the program. Next, we perform program analysis to pre-process the malicious payload. Finally, through a Monte Carlo tree search-based optimization, we will generate the evading samples. So how to construct the substitute setup? Let's assume the adversary has a copy of the program. He can do this by either with a compromised device, an insider with physical access, or some public available software. He will perform symbolic execution on the program to obtain the execution path. And for each test case power side channel signals will be collected. And these signals will be used to train a substitute detector model. To perform the malicious payload injection, the malicious payload will first be split into independently executable chunks. For example, 3 of these chunks, each one represents the modification of a critical parameter of an attitude control program. Once we have these chunks, they will be distributed into the binary program. But not all the locations in the binary program are suitable for injection due to a set of constraints. So first, the injected program needs to be free of any syntax errors. It should not crash at the runtime. Also, the malicious functionality of the malware needs to be preserved. And this is because the data a malicious chunk intended to modify or retain is only available in some locations in the program. So we introduced the concept of life range, which is defined as the available locations in the program of the data. Now that we have the malicious chunks and their candidate injection locations, we will generate the evading samples. We formalize this problem as a tree search problem. Here is an example. The capital letters represents the benign program segments, and the lowercase letters represents the malicious chunks. The goal is to inject the lowercase letters in between the capital letters. And the objective of the search problem is to find the leaf nodes that give us the highest confidence score. This problem can be solved with monocolor tree search-based optimization. We evaluate the proposed attack with the following experimental setup. For signal acquisition, we use a chip whisper light sampling at 40 megahertz, and we use a STM32F3 as the embedded device or the victim device. We use 5 representative control system softwares and 5 very common control system attacks. To construct the side channel monitor, we consider both time and frequency features and the 3 popular time series models to form the detector. We first present the results on the same device. So in this case, we're optimizing our attack on device 1 and evaluate on device 1 as well. It can be seen from the results, all the scores are significantly higher than the detection threshold. And also for some weaker detectors, the confidence score is much higher. This means that the proposed attack can find evading samples with high confidence score. We compared our attack with a baseline attack. In the baseline strategy, we just manually injected the malware as a whole into the program. It can be seen from the table that without our proposed optimization approach, injecting the malware will result in a much lower confidence scores and that will be detected. Next, we make it more challenging for the attacker. So the attacker optimized the attack on device 1, but evaluated on device 2. It can be seen from the results that the scores are slightly lower, but they're still acceptably high and also above the detection threshold. So this means that our attack can perform very well under a cross-device setup. Next, we consider an even more challenging scenario. In this case, the adversary do not even know the model, so he needs to exploit the transferabilities between different models. He will have to optimize for one model and then attack a different model. So this table represents the confidence scores between each pair of models. It can be seen from the results that the proposed attack transfer pretty well across different architecture of the same type of model, different type of the model of the same model family, for example, the neural network based. But they don't transfer so well, like between different family of models, for example, from neural network to HMM. So this means that the adversary only needs to know the family of the detector models to successfully perform the attack. Finally, we consider this most challenging or extreme scenario where we assume that defender has knowledge of our attack. So when he designed the defense system, he will include that information in an adversarial training manner. So basically, he will have one more adversarial class and put all the evading samples generated by our attack into this class. And then the augmented detector is trained with the the new data set. The attack success rate we measure here is slightly different from what we had before. We compute the number of traces not classified into the adversarial class as the ASR. It can be seen from the table that and even under this extreme scenario, our proposed attack can still find evading samples. For future work, we recommend the following ways for defense. First, the defender could potentially benefit from fusing the information from various side channels. For example, power, EM, and software side channels at the same time. Also, the success of our attack is partly due to the homogeneous nature of the signals used to train a monitor. Like if you look at the side channels for the same test case, like they look very similar to each other. So fitting a robust learning technique in this scenario by combining data synthesis and contrastive learning to train a more robust model could also help. To conclude, in this work, we study the resilience of physical side channel monitor solutions. And we found out that even though they're physically isolated, measuring immutable side channel signals, they're difficult and even impossible to be spoofed or manipulated. They're still not robust and vulnerable to advanced attacks. We developed a novel attack against these power side channel monitors and reevaluate the attack on a realistic hardware and software setup. We conclude that more research is required to defend against such advanced adversaries. Okay, thank you so much for your time. And any questions?